So where did you guys end up with Adam yesterday? From what I understand, it's going to be, let's see, this this weather packet. You guys got through hurricanes?
No.
I don't think we even started hurricanes.
Oh, okay.
Just general discussion. He left us parked under a cloud.
Parked under a cloud.
You got to this slide that you're showing right there.
Okay.
Sheer line.
So did he talk about this at all?
Yeah.
All right. Well, so is this kind of where we're at then?
I would say so.
Yeah, it looks familiar.
All right.
But if there's anything extra that you want to go over, go ahead, because my brain exploded when Adam told us that the sun affects everything.
Yeah. Well, that's pretty much it. So did he talk about what creates weather? I mean, the uneven heating of the Earth's surface?
Yeah, that's about when my brain exploded.
Yeah. So, I know up north here, and I've seen them down south, but turkey vultures, pretty common to see, right?
Uh-huh.
You can see the turkey vultures kind of just circling, lazy circles in the sky. Well, they're riding thermals, right? So that's a very good indication of what the uneven heating and cooling of the Earth's surface is doing. Is it's creating these pockets of rising air, right? And basically, large areas, let's say, as they heat and cool, it's kind of like an ice cube, right? Water. As water cools, it expands, but as it heats up, it retracts. Water, as it turns to ice, it traps in that air and stuff like that, and then it expands. But then when you heat it up, it retracts and goes back into that liquid state. Well, that's kind of what is happening all around us at all times, right? So as that expansion and contraction is happening and these pockets of hot air are rising, and as it cools, as it gets higher in the atmosphere, you're creating this rotation, whether that be a lateral rotation or a vertical rotation, is going to kind of determine what kind of weather we're going to be seeing. And, we start adding moisture to that, start going over bodies of water and things like that, then the visible, the weather becomes visible at that point. And we start seeing clouds or different types of precipitation or fog or visible moisture in some form. So yeah, I mean that's weather in a nutshell, right? But what we need to do is we need to kind of dissect it a little bit more. What's causing this different type of weather? So, is there anything that you guys had questions on coming up to this point? Any questions?
No questions. Just ready to learn more.
Yeah. So, I mean, just like water in the ocean and stuff like that as well, you know, air has the same kind of currents that you see. It's just air rather than water. But we'll just kind of talk a little bit what the different pressure systems are. Anyways, so he got all the way through TTU or TUTTs. Tropospheric upper tropical upper tropospheric troughs.
I may have dozed off. I don't remember TUTTs.
Okay. So he talked about what a low pressure, high pressure, and a trough are, right? So a trough is basically an elongated area of low pressure, right? Did he talk about the pressure systems at all, or is this just all Chinese to you guys?
He did talk about highs and lows.
Okay. Okay, so what kind of weather is associated with a high pressure?
Usually calm,
Okay. And
high clouds,
and,
Dry,
stable air.
uh-huh. And a low pressure?
rainy and stormy.
Uh-huh. Good. So when we talk about some of these different types of troughs that we see, what we're talking about is the location of the trough. So the tropical upper tropospheric trough, basically it's an elongated low pressure, and it's over the tropics, right? So places like Hawaii and stuff like that, where it's these island type weathers or island type land masses. So we'll see these tropics basically move for, like it says here, southeast or east, and then it spreads middle or high cloudiness over an extensive areas east of the trough line. Okay, so typically low pressure systems, when we look at low pressure systems, the weather, the clouds and stuff, they're going to be developing along the eastern side of the pressure system, right? So they're building, because what's happening is the low is trying to overtake the high pressure. And so what's happening is you're getting a lot of convection in those areas. So a lot of that circulation and convection. So that's why you're pretty much, whenever we associate a low pressure system, we're going to see the weather develop on that eastern side of of the cell. Okay. So, yeah, I mean, typically what we're going to see associated with this is, like it says, is the large amount of extensive, sometimes dense cirrus, and some convective and clear air turbulence often develop. So, we don't, in the regional world, we don't really deal with this much. You're going to be dealing with this a lot when you're flying over the oceans. But yeah, so did you talk about cloud layers and what the different cloud types are? Or do you guys understand what a cirrus cloud is?
We didn't talk about that.
Okay. And it's kind of hard to figure out what comes first, the bird or the egg, right? So we'll talk about cloud types and cloud formations, but cirrus clouds are typically a higher altitude cloud. Okay. You've got cumulus clouds, you've got stratus clouds, and you've got cirrus clouds. So depending on the type of cloud formation, determines the altitude typically, and how thick the clouds get. Cirrus clouds are just the high altitude clouds that you see. And we'll talk a little bit more about that, like I said. So these pressure systems, these TUTTs, we're going to see a lot of rainfall. We're going to see that convection, the turbulence, things like that. Because remember, it's a low pressure, elongated low pressure. So we're going to be seeing those pressure systems form on the eastern side of it. So. Tropical waves, also called the easterly waves. And it's really hard when I wasn't in class yesterday to know where you guys were at. So the trade wind belt, you guys talk about the trade wind belt, where that's located? Have you guys heard?
He did show us the red line on the map up above.
Mm-hmm. So the
on the map.
Does anybody know why we call them the trade winds? I mean, it's fairly descriptive in the name, right?
Isn't it the route that the slave used to take?
Yeah. Get high winds, right? So you can get moving pretty quick in those wind systems. Are you talking? So you were talking about these maps here?
Yes.
Yeah. So the trade winds, basically the Spanish used to take them transatlantic, doing trading, right? So that's just where we had a high amount of wind that really helped speed them along, right? So when we talk about the trade wind belt, it's close to the equator. But these tropical waves, so they're normally, like it says, normally occurring in the trade wind belt, but in the northern hemisphere, they usually develop develop in the southeastern perimeter of subtropical high pressure systems. So these ones travel east to west, as you can see up on that map above. And like it says, high prevailing easterly circulation of the tropics. But yeah, tropical wave, just think of it as high east to west winds that happen near the equator. So that's where we're going to see a lot of the hurricanes develop as well, right? So this just kind of shows you. Okay. So yeah, these tropical waves, we see them near that trade wind belt, right? So this AB is what's we're indicating as the trade winds, right? These bands where we'll see a strong northerly and then go to a southeasterly, right? That's the tropical wave. It's almost like riding a wave. So just like anything, when we get that extreme heating during the summer, that's when we're going to see the stronger storm systems. So these tropical waves, they occur in all seasons, but because they're near the equator, but are more frequent and stronger during the summer and early fall. So like I said before, that's when we're typically going to be seeing our hurricanes is August to October is typically our hurricane type season. So yeah, it's like it shows here. You've got a really strong buildup of convection near those tropical waves. So your clouds, yeah, the convection just means that the cloud, you've got a really strong patch of circulating air that's going high altitudes, right? So yeah. So the West Africa disturbance line. So it's similar to a squall line, but it moves from the westward, moves westward off the continent at the tropical latitudes. So, oops, gosh, that's typically when we're gonna, or you can see that line there. Let's see. All of this is kind of leading up to hurricanes, right? So this is all the stuff that's building up hurricanes, these tropical waves, these TUTTs. This is what's building up and creating those huge storm cells. So, yeah, a lot of our storm systems that develop down here in the Gulf are going to be caused by the hot, dry, warm winds coming across the Sahara Desert, and then creating that, because of how hot that air is coming across, it's creating the huge potential for convection, right, and storm buildup. So you can see that West Africa, what's it called, the West Africa disturbance line is right here, right? Builds up right off the coast of Africa, and then pushes along the equator and then up and out, right? You get really what is causing a lot of it is Africa. I mean, it's even creating all of the storm systems further over here in the Pacific. That's how strong it is. But let's see. Yeah, like it says, can eventually develop into tropical storms or hurricanes. So these tropical cyclones, this is kind of, as we've been talking about, built up off the coast of Africa, and it builds as it crosses the Atlantic. The Atlantic Ocean tends to be a lot colder than the Pacific Ocean. So you have those really hot, dry winds coming over the cold Atlantic. You see a huge amount of circulation and convection there. So this just kind of categorizes the tropical cyclones here. So a tropical depression is sustained winds up to 34 knots. Tropical storms are sustained winds up to 35, or from 35 to 64 knots, and then a hurricane is when we go 65 knots or higher. And we'll categorize the hurricanes in just a second here, but there's a slight difference between the hurricanes and the typhoon systems, right? So typhoon, we're talking about Pacific Ocean. Hurricane, we're talking about Atlantic Ocean. But it says here the term super typhoon is used when there's a maximum sustained wind of at least 130 knots. It's pretty quick winds. So the developments, the prerequisite for tropical cyclone development are optimum sea surface temperature under low-level convergence and cyclone wind shear. So this is all of what we were talking about before. The shear lines, TUTTs, tropical waves, and lines of convection in low altitudes moving from the continent to the tropical ocean. So from the African continent to the tropical ocean. The low-level convergence associated with the system itself will not support the development of a tropical cyclone. The system must also have horizontal outflow or divergence at high tropospheric levels. So still, these things combined cannot create it themselves. What we need is the high winds, right? Is basically what it's talking about. And like I said, it creates that chimney or that buildup of convection. So yeah, I mean, everything that we just talked about with the high winds coming off of Africa, that's what's creating those cells that we see along our eastern coast primarily. You know, there's an old ancient saying where the what is it the flutter of a butterfly's wings is the cause of a hurricane or something. I can't remember the exact saying. Is the cause of the hurricanes in America. It's not far off. I mean, something as little as the heat building up over Africa there. That's really what's creating a lot of the convection we see across the ocean, a lot of the storm systems. So the way we see these typically move and kind of how they build prediction models and stuff like that. So the movement, the tropical cyclones in the northern hemisphere usually move in a direction between west and northwest while in low latitudes. As these storms move towards the mid-latitudes, they come under the influence of prevailing westerlies. So as you can see, this circulation on this map up here, we can see how these storm systems, we've got these semi-permanent pressure systems, right? So typically what we're going to see is we're going to see the high pressure right here, and it's pushing the air to the south along the equator, right? And we have this pressure system that's also pushing along the same line. Well, as we get closer to the coast here, we see another high pressure here that tends to sit over the US, right? Semi-permanent pressure system. So this one is rotating as well, and it's pushing winds westerly. And you have this low pressure here, so we're just creating this huge convection oven right here, right? As the air cools, it goes west, and we just see it continue to circulate. Did he talk about the way high pressures and low pressures move? Their rotations? Because that's kind of important with all this.
Yeah, that a high pressure system goes, I want to say, counterclockwise, or it might be vice versa.
I think that's backwards. So the high pressure, and it shows it here on this map too. The high pressure, yeah, rotates it clockwise. Low pressure is counterclockwise.
Okay, yeah.
So, sorry,
Garrett.
He hit on that.
Yeah.
A question regarding direction when you're talking about wind. Because when I was watching the cursor as you were explaining off of that high-low permanent or semi-permanent chart, you were, when I saw the cursor, it was coming off the top of a high, which was circulating to the right and heading in an easterly direction. You said these are westerlies, and I want to make sure that we're all on the same page on what the difference between what is a westerly wind and an easterly wind.
Yeah, so You're talking about this right here.
Yeah, you were talking about the one, your cursor was over the one over the United States at the time.
This one.
And the one above, yeah, the arrows coming down out of Canada and heading east.
Mm-hmm. Yeah, so that's why I was asking about the pressure system. So high pressures rotate, they'll rotate clockwise and down. Okay. The low pressure systems will rotate counterclockwise and up. The low pressure is always trying to overtake the high pressure. Okay. So what's happening is this rotation here, this is rotating in a circular clockwise pattern, while you have this one rotating in a counterclockwise pattern. So what's happening is the air is heating up and it's coming down here, but this high pressure over the United States here, also rotating clockwise, is circulating air down here under this low pressure. You can see where they meet over the Atlantic Ocean near Canada here. There's basically the two pressure systems are pushing over one another and causing the wind direction to go to the east. That's an easterly. Okay. This high pressure system down here, you have a high pressure system down here, high pressure system down here. Remember, everything that we have in the northern hemisphere is going to be reversed in the southern hemisphere, right? Once we cross the equator, basically the toilets stop flushing the same way. It's same with the winds, right? High pressures and low pressures. So the high pressure here is rotating the same as a low pressure here. So it's accelerating the wind across the equator here. And the easterly's accelerating the winds across here. So these trade winds, you could see the trade winds here, right? Is where this high pressure and this high pressure converge over the equator area. So this is a westerly, and then this would be the easterly, because this low pressure is converging with this high pressure. Does that make sense?
Yes.
So, yeah. Let's see. And it's kind of interesting to see that, you know, so this is just basically a mapping of the hurricanes from the Hurricane Center. You can see that the low pressures hover over these colder air, the colder air up here, colder, drier air, where the high pressures that are, you know, moisture laden and warm are down here near the equator. And it's kind of interesting. You can see where the high pressure system tends to lie, and that's why it's called the semi-permanent pressure system. It's because you can see that there's typically a high pressure right here around that 20 degrees north latitude off the African coast. But then you can see the low pressure that tends to circulate up here and kind of channels the weather over the Pacific. It's pretty interesting.
Can you make your cursor a little larger?
I sure can. Just give me 1 second here. All right. So here you can see where the high pressure once again tends to reside, just like we see on this 20-degree north latitude, and then where the low pressures tend to reside. And you can see how that channels the air currents through the Pacific and through the Atlantic. So, and that's what it's talking about here. So, as the storm systems move towards the mid-latitudes, they come under the influence of the prevailing westerlies. And then at that time, the storms are under the influence of two wind systems, the trade winds and low-level prevailing westerlies. Okay. Trade winds, remember, travel near the equator here. And the westerlies are basically that 20-degree north latitude. They're going to be pretty close to there. So the winds kind of get trapped along the equator right there until they hit land and start cooling down. Then they circulate back up over towards Great Britain. So the storm system may move erratically and may even reverse course or circle, but finally the prevailing westerlies gain control. And the storm recurves towards the north, then to the northeast, and finally to the east-northeast. By this time, the storm is well into the mid-latitudes. Okay, that's when we see the storms start to decay. As the storm curves towards the north or the east of the northern hemisphere, it begins to lose those tropical characteristics and acquires characteristics of lows in middle latitudes. The cooler air flowing over or into the storm gradually weakens it. If the storm tracks along the coastline and over the open sea, it gives up slowly, carrying its fury into areas far removed from the tropics. However, if the storm moves inland, it loses its moisture source and weakens. So that's why we see them die down right here, is because of two things, right? The decay, right? There's two things that storm systems need to build. One is moisture present, and then the other would be heat, right? That rising and falling action, the convection. Okay, so sorry, I'm trying to log on with my iPad here too, just to make sure, just to help me keep track of any comments or anything, because I'm on a smaller computer today. Okay. There. My bad. All right. Let's see. So we see those tropical storms decay really rapidly as they make landfall. The other thing that we see is when they hit this low pressure of cooler air to the north, then it also kills the storm. That's kind of why we saw, what was the name of the hurricane this last summer that was devastating? Harvey? Was that the one that was headed towards Florida, the west coast of Florida? From what I understand, the reason why that storm ended up impacting Florida at a lot less of an intensity than they had originally thought was due to how hard and how much time it spent over the dry land here. It really killed the storm, and then there wasn't enough heat to keep it building as it crossed the Gulf. So basically the things that'll suffocate it is you lose the moisture over the land, or you cool the air, and it'll kill that storm system. So once it moves outside the middle once it moves to the middle latitudes, then it turns, rather than a tropical, it turns into an extratropical, being outside the tropics. It's kind of a gee golly there. Weather in the tropical depressions, it's basically the developing stages, right? So we'll see numerous showers, thunderstorms, rain, but it's still scattered, right? When it turns into the tropical storm, that's when we start seeing that heavy cyclonic flow. And the thunderstorms and rain showers start forming in those broken or solid lines, and then paralleling the wind flow that is spiraling into the center of the storm. So that's when you see, as the storm continues to build and build and build, we start seeing that circular rotation. And once we have that cyclonic flow, then we have a tropical storm and possibly a hurricane. Like it says here, they usually form the eye of the storm in 48 hours of the cyclone reaching tropical storm strength. In the eye, it's kind of like, have you guys seen Twister with, what's his name? John Travolta? Is that who it was? It wasn't Travolta, was it?
No.
I can't remember who it was. Anyways, there's a part where they're...
Bill Paxton.
Bill Paxton, there we go. Man.
He doesn't dance as well as me.
My puppies did not like your answer.
I knew it was wrong when I said it. But anyways, the kind of near the end of the show, not to spoil anything for you guys, they go into a tornado, and they're in the center of this tornado. and it has an eye of the storm where it's like clear and beautiful and birds chirping, and then all of a sudden the eye passes them and it's total hell again, right? Well, in a hurricane, that actually happens where the eye of the storm is tranquil, calm winds, um, typically sunny, but as it passes over you, then all hell breaks loose again. Um, so, like it says here, the average diameter of the eye of the storm is between 15 and 20 miles. But sometimes it's as small as 7 miles and rarely more than 30 miles in diameter. We're talking a pretty big storm system there. 30 miles for the center. And then surrounding the eye is a wall of clouds that may extend above 50,000 feet. So I don't know if Adam talked about where weather typically is. It's typically in the troposphere, right? So the troposphere is that lower layer of atmosphere, and typically it extends anywhere from 30 to 60,000 feet. Depends on the pressure systems and stuff like that. But like 35,000 feet, I would probably say. But anyways, above the troposphere, there's typically no clouds or anything like that. Well, hurricanes can be the exception to that rule, just because of the amount of pressure in the system. So, kind of like in Twister, the eye passes over and then it's just like pure hell. It's the same thing. Wall of clouds, that's where we have the heaviest rain and the strongest winds. The maximum wind speeds we typically see are 175. That's insanely fast winds. So this is a radar image of Katrina. You can see the eye. You can see how tranquil it is. And not a whole lot going on. But then you can see this pressure, or this area of intense rain and intense convection to the north side of the eye. As it passes over you, once again, it kind of dies down, but pretty intense system. I got to Pensacola, Florida not too long after Katrina hit. It's kind of crazy to see the base was still undergoing construction from trying to rebuild from Katrina. But so this is a satellite image. Radar images, all we're going to see is we're going to see the echo from the precipitation, right? So the more dense the echo, the darker the color. Well, this is a satellite image, so this is just like a actual picture. And yes, it actually does say Florida across Florida when you're at 120,000 feet. So big white bold letters. They just want you to know that it is Florida there.
Written in snow, right?
Yeah. Yep. But yeah, you can see, it's kind of cool. You can see the eye, it's like sunny daylight in the eye there. And you can see the band of really heavy clouds just around the eye. So NOAA, kind of a side note, they own what's called an RQ-4 Global Hawk. And I used to work on the Global Hawk project. Let's see. Show you guys what it is. So this is actually the NASA. So NASA owns the Global Hawk, but NOAA uses this Global Hawk. This is the actual one that I did work on. But we built a lot of the internal components on the aircraft. They're called data links, and basically it's what links the aircraft to the ground systems and controls all the different aspects of the aircraft. The brain system, the antenna, all built by the company I worked for. Anyways, NOAA was doing this big project for NASA, NOAA was renting the Global Hawk from NASA, and they were doing this big project, and what they did is in the back here, they built these little pods that would shoot out sensors. Going back to my Twister reference, these little tin can sensors. No. But what they would do, what they were doing was they were flying over hurricanes and dropping these sensors down into the hurricanes to get readings from them. And anyways, my buddy was there. He had done the install and was doing the test flight for them. Let's see if they got a nice big picture of the NASA. Have a good picture of it. Anyways, so my buddy was sitting in the control room while they were flying the mission. And they're just flying along. It's like 70,000 feet. This thing's flying along. In the military, they use it for high altitude reconnaissance. If you guys know what a U-2 spy plane is, basically it's the drone version of a U-2. And they're flying it over this hurricane. And the people in the control room are, they're sitting in this 72-degree office at a computer with a keyboard, and that's what they're using to command the Global Hawk. They have a headset on, and they're talking to air traffic control and stuff like that. Anyways, this air traffic controller gets on. They're like, "What are you doing above that hurricane? Isn't that pretty turbulent up there?" The guy gets on, and he's like, "No, it's actually nice and calm, 72 degrees. It's perfect weather." The controller gets back on. "You got to be kidding me, right?" It's like, "No." It's like, "I'm sitting in an office, Central California." It's like, "This is a drone." The controller, "Oh, that explains it." But kind of a fun story. But yeah, it was fun being involved in that project. It's pretty cool.
So Garrett, do they use dispatchers for those?
Yes, but yeah, it would just be a job. You'd have to have a security clearance and everything to get a job and go through NASA. The what's kind of interesting about the drone area of aviation, unmanned aerial vehicles, is they're becoming extremely popular in a lot of ways, and I wouldn't be surprised to see several job opportunities pop up for dispatchers in that area. But like the Border Patrol uses drones. Several different police forces across the country will use drones. They're ex-military drones typically. But yeah, still require, to operate under the same rules as a manned vehicle would be, as far as those bigger drones. So, yeah. So this is just a chart that identifies what we classified the different category of hurricanes are. As you can remember, Harvey got up to Category 5 when it hit Houston. That's wind speeds greater than 137 knots or 157 miles per hour. Basically, it means absolute destruction of almost every type of building. Framed homes, mobile homes get wiped off the face of the earth. Extensive damage to roofs, windows, doors. Huge amounts of windborne debris. What's interesting is a lot of the damage isn't necessarily due to the wind speed itself. It's due to the pressure changes. When we have those systems go over, we'll talk a little bit more about barometric pressure, but there's rapid changes in pressure. And the wind is doing a lot of damage, but then the rapid change in pressure that's happening at the same time is causing a lot of destruction as well, kind of aiding the wind to do its job. But anyways, yeah. So let's talk about Arctic weather. Just talked about tropical weather. Let's move up to the Arctics. So this is technically the Arctic Circle, Arctic zone. Lots of ice cream. Santa lives right there, but their shakes are killer up there. But yeah, typically what we see in the Arctic as far as weather goes is we're going to see low pressure systems. We're going to see a lot of cold, dry air. It's largely determined by the amount of energy received from the sun. And terrain, basically. So the long days and long nights. So depending on how far you are from that Arctic Circle will determine the length of the days and nights. I know my friend that lives up here in this northernmost corner of Alaska, Barrow, Alaska. He'll go 21 days without any light, any sunlight whatsoever, and then they start getting little bits of light progressively. They get a little, like 15 minutes more light each day until eventually the sun never sets for basically the same amount of time during the summer. But there's a profound seasonal change in the length of day and night occurs in the Arctic because of the Earth's tilt and its revolution around the sun. So in the Arctic Circle, winter days, like I said, it won't dip below the horizon. The sun won't dip for 24 hours of sunshine. And the closer you get to the Arctic Circle, the more days you have. I know in Barrow, he said it's about 21 days of light and 21 days of darkness. So it just depends. But it alternates every 6 months. Land and water. A large part of the Arctic Ocean is covered throughout the year by a deep layer of ice, known as the permanent ice pack. This ice pack goes through a seasonal cycle where ice melts in the spring and summer and increases in the fall and winter. Even though a large portion of the Arctic Ocean is ice covered through much of the year, the ice and water below contain more heat than the surrounding cold land, thus moderating the climate. So, kind of interesting. The water is warmer than the land around it, under the ice. Pretty interesting. Temperature, it's pretty cold. There's times when my friend will be like bragging on Facebook because temperatures are warmer in Barrow for a couple days than they are down here in Salt Lake. It just depends. But there's also those days that he sends pictures and it's negative 50 plus degrees and he's completely covered in the full Eskimo garb, you know, and on his snow machine. And I think the trade-offs for his 1 week of glory versus my nice long summers, I'll take it. But anyways. Cloudiness over the Arctic is maximum during the wintertime due to the ice pack being more widespread. Spring brings many cloudy days, and the cloudiness is at its maximum in the summer and fall. Like we've talked about before, the more water, the more potential for clouds and different types of moisture to form, right? Or I mean, different types of storm systems to form. So, they'll also get those polar lows. Polar lows are small, intense, low-pressure systems that can develop rapidly when cold air flows over warm water. They produce severe weather, strong surface winds, and heavy precipitation. But once again, they kind of kill themselves, suffocate themselves once they get over the land. In the Arctic area, like I said before, it's going to be mostly dry. There is some precipitation. These polar deserts are pretty widespread. But typically the only type of precipitation that they really get hit with is going to be snow. And it's going to isolate itself mostly over those polar caps. So, typically the winds are light, but we do have those polar lows once again. But once again, you can see the trend. Strongest during the summer and fall when they have the heat. Heat causes a lot of the circulation and storm systems that we see. I mean, the Arctic's pretty boring for weather, to be honest with you. It's just cold and dry, just as we said before. When it heats up during the summer, that's when they see most of their weather. But for the most part, it's just going to be cold and dry year round due to the amount of time that they, or how north the latitude is, right? And its distance from the sun. So, did Adam talk about occluded fronts?
I don't believe so. No.
So occluded fronts are where we have basically the lows and the highs converging, the high and low pressure systems converging. So typically what we see in an occluded front, we'll see low clouds, precipitation, poor visibility, and sudden fog formation. Fog formation typically over the coastal areas, but yeah, those low clouds, that's when we're going to be getting those IFR conditions and poor visibility. So, but yeah, the important thing to remember with the occluded front is when it's basically a stalemate between a high pressure, or a warm front and a cold front. I'm sorry. So, a lot of times what we see as far as low visibility is temperature inversion. This is something that you're going to be asked about on the practical is temperature inversions. So basically, the way temperature goes is the closer to the ground, the warmer the temperature. As you rise in altitude, the colder the temperature, right? Well, what will happen is we'll have a reversal of that, where the warm Now, I kept getting this mixed up last class because I'm trying to explain it and do it all without confusing myself. It's really hard to do. Yeah, the cold air. So you have a warm pocket of air that overtakes a cold pocket of air. So you have the colder temperatures down lower to the ground, and the higher you get in altitude, the warmer it gets. So inversions can slow down surface winds and trap pollutants, which is the problem with Salt Lake. So kind of important to write down what I would write down to help you guys with studying. Is a temperature inversion is a warm pocket of air overtaking a cold pocket of air. So as you rise in altitude, the temperature gets warmer. So not that it really matters, but to us, that get a lot more light reflection due to the snow-covered surfaces. And then the light from the celestial bodies is a lot more brilliant, a lot more intense. So weather hazards, typically it's going to be visibility restricting phenomena, blowing snow, icing, frost, lack of contrast. So whiteout conditions, those are scary, right? Fog and ice fog. So when we're talking about fog, there's a couple different types of fog. Ice fog being one of those. So basically what creates fog is we have the dew point and the temperature reach the same level. So let's say the temperature is 4 degrees, the dew point is, and when I say dew point, that's the point at which the air is saturated. So the temperature at which the air is saturated and creates visible moisture. That's the dew point. So when the dew point and the temperature are at the same temperature, that's when we see the creation of fog. So, and that's where the water is suspended in the air. Water droplet fog occurs in the coastal areas during the summer. Ice fog is ice crystal fog. So this is freezing fog. This is fog that creates these what we call supercooled water droplets. So what happens and why the freezing fog is dangerous for aircraft is the water. Have you guys ever seen that a video of somebody dumping out a bottle of water and it turning to ice as soon as it makes contact with the plate? Have you guys seen that at all?
Yeah, I've seen that.
Yeah.
Yeah, so that's what freezing fog does, is as soon as the fog comes in contact with the surface of the aircraft, it instantly turns to ice. And ice is, once again, super bad for airplanes. So we don't really care about the size of the microns nobody cares, unless you're an actual meteorologist. But pretty dangerous stuff. So, like it says, ice fog is rare at temperatures warmer than negative 30 degrees C, and increases in frequency with decreasing temperature until it's almost always present in temperatures of negative 45 degrees in the vicinity of the source of water vapor. So, bad stuff. Blowing and drifting snow, big problem. Huge issue for visibility. Those strong winds that'll happen, those polar lows, when they hit, those high winds will pick up a lot of snow, and the blowing snow is wind-driven falling or accumulated snow that reduces surface visibility. So makes it really hard to see near the surface. Frost, bad stuff too for airplanes. Basically, our main concern when we are in the cold temperatures of the Arctic is icing, right? So icing being 10 degrees Celsius or below and visible moisture present, anytime we have those situations, we've got to immediately start thinking about ice and accumulation on the aircraft. Another issue that we see with those two different types of weather is, icing weather, is it can also, we have water on board the aircraft, potable water, and holding tanks. So we can also see problems with, those lines breaking if it freezes overnight. Things like that. We got to start thinking about things like that when we're dispatching, and we see those weather conditions. So, yeah. So, let's see. We've been going for an hour and a half. Why don't we take a dinner break here, and we'll jump back on at 7:30. All right, is everybody back?
I'm back.
Sounds like we need to give them just a minute more. Anybody other than Carrie back?
I'm back.
Here.
There we go.
I am back.
Okay.
All right. So let's start talking about the Earth's atmosphere. So what is an atmosphere? It's just basically a cloud of gas and suspended solids extending from the surface out thousands of miles, becoming increasingly thinner with distance, but always held together by Earth's gravitational pull. So we got multiple layers, right? I'm sure you guys studied those in school. The Stratosphere, and Troposphere, and Tropopause, and the Stratopause, and blah, 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 right? So one thing that I guarantee you will be asked on the practical test is going to be, what is the composition of the Earth's atmosphere? So what is it all made of? Well, believe it or not, we breathe mostly nitrogen. Now, we don't use it for the most part, but oxygen is only 21%. So you can see that 99% of our atmosphere is nitrogen and oxygen. So what you need to write down for when you get asked this question is the Earth's atmosphere is 78% nitrogen, 21% oxygen, and then other trace gases. It's not going to make you memorize this entire list, but that's pretty much it. 78% nitrogen, 21% oxygen. You can say 1% argon too, and then trace gases, but yeah. So, what is an air parcel, right? So an air parcel, kind of like how I was talking at the beginning of this course, week 1, right? We were talking about parcel of air, basically a cylinder of air, to which the basic properties of the atmospheric air may be assigned. So an air parcel is large enough to contain a very large number of molecules, but small enough so that the properties assigned to it are approximately uniform. So basically just a cylinder of air given somewhere in the atmosphere, right? So vertical structure is the Earth's atmosphere is subdivided into 5 concentric layers. Based on the vertical profile of an average air temperature changes, chemical composition, movement, and density. Each of the layers is topped by a pause, where maximum changes in thermal characteristics of chemical composition, movement, and density can occur. So like I was saying, the troposphere is what contains most of our weather, most of the the air that we breathe, everything like that, right? That's where all of, basically everything on the Earth lives is going to be in the troposphere. Then, when it talks about the pause, that's where all these changes occur between the 2 layers. So you see, this is where we see those big changes in the thermal characteristics, chemical composition, movement, and density. Okay. So for each layer of atmosphere, there's a pause around it, and then the next layer of atmosphere, kind of like a jawbreaker, right? I remember getting those massive jawbreakers and taking an entire summer to get to the center. But that's exactly how the Earth looks once you, if you break it down into, you know, the different types of atmosphere and things like that. So, so let's talk about the troposphere. So it begins at the Earth's surface and extends up to about 36,000 feet high. Okay, so that's the average height is going to be that 36,000 feet. As the gases in this layer decrease with height, the air becomes thinner. Therefore, the temperature in the troposphere also decreases with height. As you climb higher, the temperature drops from about 15 degrees C to about negative 56 degrees Celsius. Okay. Almost all weather occurs in this region. So let's see. All right. So we'll get into it, I'm sure. The vertical depth of the the troposphere varies due to temperature variations, which are closely associated with the latitude and season. It decreases from the equators to the poles and is higher during the summer than it is during the winter. At the equator, about 18 to 20 kilometers or 11 to 12 miles high, at 50 degrees north and 50 degrees south latitude, it's only 9 kilometers or 5.5 miles. And then at the poles, it's about 3.5 miles high. Okay. Kind of interesting to see, when we talked about tropical weather and then we talked about Arctic weather, kind of interesting. You start putting the puzzle pieces together, right? The reason why the Arctic doesn't have nearly the weather that the tropical regions have is because of the depth of the tropopause. And it's on this first picture here. So this is the troposphere, right? We have the 3 different layers, right? This first layer, like it said, is going to be that 18 to 20 kilometers thick, versus here, where it's going to be approximately, what did it say? 5.5 miles. And then up at the top, it's going to be 3.5 miles. So you can see how those really violent storms have a lot more room to gain momentum and to gain severity in this region than they do up here in this region. Kind of interesting, right? Sorry, let's get back down to here. Okay. The transition boundary between the troposphere and the layer above is called the tropopause. Both the tropopause and troposphere are known as the lower atmosphere. Okay. So, main thing to remember about the troposphere, that's where almost all of Earth's weather happens. So, one thing that you'll find, that I find interesting at least, is on our, let's go to, Let's pull up a flight release real quick here. All right. So this MWL here, that is the height of the tropopause. Why do you think that'd be important for us to know? Kind of already touched about it, or touched on it. 37,000 feet, 37, 37, 37, along the length of our flight. Anybody? Why do you think it's important to list that on our flight plan? Somebody just take a stab.
Something to do with cabin pressure?
So it's more to do with weather, right? We know that pretty much all the weather exists in that troposphere. And so when we know that the height of the troposphere, or the height of the tropopause, is 37,000 feet, it's a good bet that we're not going to have convective activity above that. We're not going to have storm systems building above that, right? So kind of an interesting little tidbit. We can look up and we can see where the tropopause is on flights, and they may be experiencing clear air turbulence. They may be experiencing, bumpy rides. We can look at our flight levels and we can go, oh, look, if you climb up to, you might want to try climbing up to 36,000 feet. You may get a little less bumpy at that altitude. May smooth out a little bit. Things like that. So stratosphere. Stratosphere is on top of the tropopause, right? So we got the troposphere, tropopause, stratosphere. Okay, the stratosphere extends from the tropopause up to 50 kilometers or 31 miles above the Earth's surface. This layer holds 19% of the atmosphere's gases, but very little water vapor. So remember, things that the storm systems need are water vapor and heat, right? So you can see why we don't really see storms or don't see cells build in the stratosphere. Temperature increases with the height as radiation is increasingly absorbed by oxygen molecules, leading to the formation of the ozone. Temperature rises from an average of 56.5 degrees Celsius at the tropopause to a maximum of about -3 degrees Celsius. So it gets pretty warm up there, right? This is due to the ultraviolet radiation. So it keeps things nice and calm up there. Commercial aircraft often cruise in the lower stratosphere to avoid atmospheric turbulence and convection in the troposphere. So just what we were talking about in the flight plan, right? Severe turbulence during the cruise phase of the flight can be caused by the convective overshoot of thunderstorms from the troposphere below. The disadvantage of flying in the stratosphere can include increased fuel consumption due to warmer temperatures, increased levels of radiation, and increased concentration of ozone. So when we look at, it's talking about ozone and things like that. There are times where the ozone layer will get extremely low to the ground. We're talking at like 25,000 feet. And in order to fly through ozone, we have to have ozone scrubbers on the aircraft. Ozone is pretty bad for humans, right? It I believe the effect of the ozone is that it basically is looking for an oxygen molecule. What is it, O3? Is that ozone? It's looking for an additional oxygen molecule. Or is it O1? I don't know. Anyways, it's looking for an additional oxygen molecule. So basically what it's doing is robbing oxygen from us and suffocate. So you need to have ozone scrubbers on the aircraft, or else you cannot fly through ozone layers. They typically are up northern. The reason why we see them drop so low is, if you remember, the tropopause is, or the troposphere is a lot thinner at the Arctic, at the poles, right? And remember, the ozone we typically see associated with the stratosphere. And so where we typically see these ozone problems occurring is going to be over like Canada, Alaska, and basically in order to fly in the area is you just have to be below the ozone layer. And that's, yeah, like I said, it's due to the hazards it causes to us, but occasionally we see these ozone layers come in to the northern United States. We've had them descend down into like as low as Missouri area and cause a lot of problems for aviation. I know it shut down flights for multiple days before at SkyWest through the area due to it being so low. But as you can see here, this is the temperature scale, right? So depending on where these different layers are, will determine where or the temperature changes. So we're talking about in the troposphere, weather's occurring typically in the troposphere. And we start around 15 degrees Celsius at sea level. That's our standard temperature. As we climb and gain altitude, you can see that this is kilometers above the Earth's surface. So at around 35,000 feet, we can see this temperature shift. So we won't get any colder than about 56 degrees to 60 degrees C at around 36 to 40,000 feet. Then, as we continue to gain altitude, we will see the temperature shift the other way, right? Remember, those oxygen molecules are grabbing ultraviolet radiation and basically heating up this layer. But this layer is very calm and typically there's not a whole lot going on, right? Very little water vapor, and hardly ever do we see any storm systems extend up into the troposphere, up into the stratosphere. The mesosphere, though, as we continue to ascend higher and higher, we see a drastic decrease in temperature. Our lapse rate for standard temperature drops is significantly higher than it is down here in the troposphere. We lose a lot more temperature quickly. But once we get above the mesosphere, and get into this thermosphere, we see an increase in temperature again with our height. Okay. And you can see here, this is, the height of Mount Everest is well within the troposphere. This is where most aviation occurs. The stratosphere is where we typically, weather balloons, things of that nature. That's typically where they hang out. Meteors, where we start seeing the debris turn into meteors and disintegrating in the atmosphere, is going to be in the mesosphere, starting in the mesosphere, descending down into the stratosphere, right? And sometimes coming all the way down to the Earth's surface, being called a meteorite. Aurora borealis, caused by solar flares, is typically going to be happening in the mesosphere. My buddy in Alaska, he's got some absolutely incredible pictures of the Aurora borealis, but really pretty. But then you can see space shuttle satellites are typically flying in the thermosphere altitudes. And then we have the exosphere. So the mesosphere extends from the stratopause to about 85 kilometers, 53 miles above the Earth. Gases, including a number of oxygen molecules, continue to become thinner and thinner with height. Oxygen, when we talked about at the week one, I was telling you guys about grabbing a parcel of air and let's grab this parcel of air here. It's kind of like a tube of feathers. If we just start throwing feathers in the top here, as we put more and more feathers in, they're going to compact tighter and tighter down here at the bottom. We're going to have a lot more feathers in this area. But as we continue to put feathers in and continue to move up this cylinder, we start seeing fewer and fewer feathers until we get up here at the top where there's only like 2 or 3 feathers, right? So it's the same thing with the atmosphere. These oxygen molecules are a lot tighter and a lot closer together the closer you are to the Earth's surface. But as you continue to move higher and higher in the atmosphere, those oxygen molecules get more and more spread out. The thinner and thinner the layer is. So So that's going to be important when we talk about like standard lapse rates. We start talking about you know, things of that nature. We talk about atmosphere and things like that. The gases, including a number of oxygen molecules, continue to become thinner and thinner with height. As such, the effect of warming by ultraviolet radiation becomes less and less pronounced, leading to a decrease in temperature with height. On average, the temperature decreases from about 3 degrees Celsius to as low as negative 100 degrees Celsius. Okay. So it gets really freaking cold up there in the mesosphere. So, however, the gases in the mesosphere are thick enough to slow down meteorites hurling into the atmosphere, where they burn up, leaving fiery trails in the night sky. Did you guys all get to see the Red Bull Felix Baumgartner jump from 120,000 feet? Has everybody seen that?
I have no idea what you're talking about.
No,
I
I have not.
recall seeing
I
that.
don't think so.
So he's the
It's like
first.
the jump from the balloon.
Yeah, he jumped from a weather balloon, basically. So it was the highest at the time. It's since been broken, but at the time it was the highest free fall ever recorded. So he jumped and he actually broke the sound barrier on his descent. So he jumped from 120,000 feet. Now, I don't know the conversion into miles. That's going to be... So 21 miles, almost 20 and a half miles. Anyways, like I was saying, on his descent, so he was jumping from basically this point here, somewhere in here, and on his descent, because of how thin the oxygen and other gases are, he picked up speed to, I can't remember what they said his miles per hour were. It was somewhere in the neighborhood of like 680 to 720 miles per hour. If you guys look it up on YouTube, it's really cool. I remember watching it live, just being absolutely blown away. There's a guy that had, what was his name? Kelly Kittinger or something Kittinger, who had jumped years prior to it, back in the 70s, I want to say, late 70s, early 80s. And Felix Baumgartner was the first one to attempt a high altitude jump like that, high altitude free fall since him. But
Showing from 128,000 feet.
yeah, there you go. 128,000 feet. Somebody look. Are you looking it up right now?
Yes.
Yeah. Does it say his final speed?
I can briefly scan it if you'd like me to.
Yeah, if you would.
It says reaching an estimated speed of 833.9 miles per hour.
So a lot faster than I thought.
Yeah.
Anyways, in a normal free fall, we hit our what is it called? The terminal velocity. Terminal velocity in the troposphere, average sky jump from 13,000 feet is going to be about 120 miles an hour. Right? That's due to the amount of air pushing against us. So the air's kind of holding us up. Well, from 128,000 feet, there's a lot less of that resistance, a lot less of that friction. And so, that's how he was able to go so fast. Looking at the space shuttle on reentry when it's entering the Earth's atmosphere is doing something like Mach 17 times the speed of sound as it descends. As it gets closer, as it breaks through like the tropopause, it slows down to, a much, much, much slower speed. And a lot of that's due to the amount of friction in it and on the aircraft. So due to the air, the outside air and everything. So pretty insane. I know that DARPA is working on an aircraft that it's an unmanned vehicle that travels at Mach 17 and it stays in the stratosphere. But pretty crazy what, you don't realize how much friction there is until, just with air where we're at now, how much friction that can cause at higher speeds. And, when we're talking about developing aircraft, these aeronautical engineers and stuff, overcoming things like the sound barrier, how big of a feat that really was. And a lot of that's due to the friction of the air and trying to break free of that grasp. But yeah. Anyways, so the thermosphere. Again, this is where like the space shuttle hangs out. A lot of our satellites. Extends from the mesopause to 690 kilometers or 430 miles above the Earth. Typically, what does anybody know off the top of their head? The orbit of the Space Shuttle and International Space Station. I want to say they sit around 120 miles above the Earth. But yeah, so basically outer space right here, thermosphere. So
That's 248 miles.
248. Man, I'm just off tonight.
Maybe they are.
No, that's kind of like the one guy in the choir singing out of tune, blaming everybody else, right? No, the so once again, everything becomes increasingly thin, but because only higher energy ultraviolet and X-ray radiation from the sun is absorbed. But because of this absorption, the temperature increases with height and can reach as high as 2,000 degrees centigrade, or Celsius, I'm sorry, near the top of this layer. Despite the high temperature, this layer atmosphere would still feel very cold to our skin because of the extremely thin air. The amount of energy from the very few molecules in this layer is not sufficient to heat our skin. So, kind of crazy to think about, right? Kind of mind-boggling.
When we watch all of those Hollywood blockbusters and see people in space frying from the sun, that's not necessarily true.
Yeah. Yeah.
Awesome.
Yeah, the air's still too thin for it to really affect us. Feel cold rather than hot.
I guess that would depend on which planet you're on and what the atmosphere is like there.
Yeah, exactly. But yeah, kind of interesting. 2,000 degrees centigrade or Celsius. Gosh, I keep saying that.
Thanks for bringing up a memory from my childhood watching the movie. Now I won't be able to sleep again.
Sorry, Rex.
What movie's that?
I just remember a guy stepping out of the shadows when he was on some planet, and he disintegrated, basically burned up in the sunlight.
That's awesome.
It actually.
Go ahead.
I just said it actually was awesome.
How about? But yeah, I mean, you think about, like Mercury and Venus and those, their atmospheres are extremely thin, and they're also extremely close to the sun. So, kind of interesting how hot those planets are. Yeah. So the exosphere, the outermost layer of the atmosphere, extends from the thermopause to 10,000 kilometers or 6,200 miles above the Earth. In this layer, the atoms and molecules escape into space, and satellites orbit the Earth. Transition boundary that separates the exosphere from the thermosphere is called the thermopause. So, not a whole lot going on out there. A couple satellites, some space garbage, and stuff like that, but yeah. Okay, so standard atmosphere. So we're going to talk about standard atmosphere a lot in this class when we get to the flight planning. So please take good notes on this. Continuous fluctuation in the atmospheric properties create problems for engineers and meteorologists who require fixed standard for reference. To solve this problem, they defined standard atmosphere. So this represents an average of conditions throughout atmosphere for all latitudes, seasons, and altitudes. Okay, so when we talk about the standard atmosphere, we're going to refer to this as ISA, International Standard Atmosphere, okay? Like it says here, this is just taking, depending on the elevation, the the latitudes, the season, altitudes, all of those are going to be compiled together, and they make what we call the International Standard Atmosphere, okay? So it's vertical distribution of atmospheric temperature, pressure, and density that by international agreement is taken to be a representative of the atmosphere for purposes of pressure altimeter calibrations, aircraft performance calculations, aircraft and missile design, ballistic tables, etc. Weather-related processes are generally referenced to the standard atmosphere, as are examples of this document. Okay, so what it's saying is there is no way to say this in this area, this is the norm. You know, it would make everything way too complex if across the country we had to, you know, change our standard if we were moving from one side of the continent to the other, or country to country, or transatlantic, trans-Pacific. It would be way too complex of a system. So they came up with an international system. And, you know, we talked about this a little bit, but basically the system allows us to calibrate our altimeters to the same setting, so everybody's flying at the same altitude, or, you know, the spacing is all the same. Whether when we go to 18,000 feet and above, we switch over to the standard altimeter of 29.9 or 2. And what that does is that makes it so that regardless of, you know, what's going on inside your cockpit or where you are, your aircraft is always going to, and the aircraft, other aircraft around you are always going to maintain that same altitude, with the proper spacing. So it's the way we calibrate all of our instruments, or all of our altimeters in every aircraft. Like it says, for aircraft, missile design, ballistic tables, everything like that. Okay. So this is the standard atmosphere. Okay. We are always going to refer to Celsius when we refer to our standard atmosphere. Okay. This is sea level temperature. Sea level pressure, we're not going to talk about hectopascals. We're always going to talk about inches of mercury. Okay. So this is our standard. Okay. It says here the lapse rate of temperature in the troposphere, 6.5 degrees Celsius per 1,000 meters, 3.57 degrees Fahrenheit per 1,000 feet. Okay. We don't, our standard lapse rate that we use in aviation is going to be 2 degrees Celsius per 1,000 feet. Okay. So don't just ignore those ones. For the purposes of aviation, 2 degrees Celsius per 1,000 feet. I mean, 2 degrees Celsius per 1,000 feet. Okay. We don't use meters. We kind of do a transition. Okay. So do the math. Okay. If we ignore this part, can anybody do a quick translation or conversion? Sorry. So take 3.57 degrees and turn that into Celsius, from Fahrenheit to Celsius. That's not what I wanted. So 0.5556. So we got to multiply it by 3.57. So 2 degrees Celsius. So it is that, but do you guys see? So why I say 2 degrees Celsius per 1,000 feet. So everything that we do in aviation as far as reading weather, it's always going to be put out not in Fahrenheit, but in Celsius, okay? But we don't go in meters, we go by thousands of feet. So it's kind of a mix of the two. Because we don't use Fahrenheit in our weather charts, and we don't use meters in our measurements, we've got to basically Frankenstein the two. 6.5 degrees Celsius per 1,000 meters equals 2 degrees Celsius per 1,000 feet. Have I confused you? This is the problem with the United States right now. If we would have just started using the metric system rather than the imperial, we would have been so much better off. But no. Came up with our own stuff, huh? Everywhere else in the world is using metric. Okay. Temperature at the tropopause, 56.5 degrees Celsius or negative 70 degrees Fahrenheit. Okay. The tropopause, that's also where we see it kind of flatline on our temperature, right? So you can see here, oh, this graph just represents the lapse rate, standard lapse rate, and standard atmosphere in the troposphere.
Yeah. Do I need to wear a dress for the?
What?
Do I need to wear a dress for the temple thing?
For the interview? I would. Whenever I meet with the bishop, I always get into something a little nicer.
I'm confused. Are you telling the whole class to wear a dress?
Everybody heard that?
I bet these fellas would look real good in blue.
Wait,
I always wear a dress when I meet with the bishop too.
Yeah. My daughter's turning 12.
Keeps me from getting any callings.
So she's going. But sorry about that.
That was very sweet.
We hear the conversation.
But kind of funny story is my daughters play softball. And last year, well, I've coached them for several years, but last year we were in All-Stars tournaments, and we had an All-Star tournament where we were kind of the underdogs, and I told the whole team, look, if you guys like place in the top 3 in this tournament, I will wear a dress to the next tournament.
That was funny. You looked through.
And so
it was hilarious.
they ended up placing 3rd, and I wore a dress the entire next tournament. So, and I did look good.
Awesome. I love it.
I sported it, and I had a couple umpires walk up. What the hell are you doing in a dress?
Now, full disclosure, Ash, you have to let people know that you are from the Bay Area.
Yes, I am. Born and raised.
Oh, man. Anyways. Yeah, so there we go. So standard atmosphere, we're going to be using that a whole lot when we're doing our flight planning, okay? We're going to do our standard atmosphere. We're always going to figure out what our standard atmosphere is, and then we're going to figure out what our deviation from standard atmosphere is. So I'm just going to kind of show you guys real quick what that looks like. Pull up some stuff here. Oh, I thought I just updated this. There's Ash. No, just he's, I don't know. Mike Thompson, really cool guy. Like Mike. Uh-oh. So, when we're doing our flight planning, let's look at well, heck, let's go to St. George. Okay. We're going to look at our winds and temperatures aloft, and we'll pull up the METAR too. Oh. There we go. Okay. So, our current temperature here in St. George is 29 degrees Fahrenheit, or Celsius. 29 degrees Celsius, okay? So, I take 29 degrees Celsius, and my tablet, I'm going to pull up sky vector really quick. Look at St. George, because I need to get the altitude of the airfield. All right. St. George St. George Airport sits at 2,884 feet. Okay. For flight planning purposes, we always round to the nearest 500 feet. So we'll just say St. George Airport sits at 3,000 feet. Okay. What we do is, if you guys remember me saying, we'll take this 3,000 feet and we will, so we're climbing. Remember, our standard temperature at sea level is 15 degrees. Okay. As we ascend or climb up in altitude, so we're 3,000 feet above sea level here, right? We lose 2 degrees Celsius per 1,000 feet. So that's 6 degrees, right? So what we do is we take 6 degrees, so we go 3,000 feet. We know that that's 6 degrees less than standard. We'll take 6 degrees, subtract it from 15, and that gives us 9 degrees Celsius is our ISA at St. George. Okay, this is our standard temperature at St. George. Now, when has St. George, even during the winter, been 9 degrees Celsius? Just teasing. You can see we're quite a bit above that right now, right? So what we need to do for performance, figuring out our performance, we need to figure out the deviation from standard temperature we are. So we would take 29 degrees. We're 29 degrees warmer. And we'd subtract the 9 degrees from it. Our deviation from standard temperature is 20 degrees Celsius, okay, in St. George right now. So that's the performance chart that we'd use, is we're 9 degrees warmer than standard. So we use the plus 20. The way we will refer to that as when we're flight planning is ISA plus 20. Standard temperature plus 20 degrees. That's going to make a lot of sense to you guys when we start flight planning. So, I just showed you guys how to figure it out. Somebody want to tell me what ISA is at 34,000 feet? I'll tell you a really easy way to figure this out.
Minus 53.
How did you get it?
How did I get it?
Mm-hmm.
I took standard and went up 34,000 feet. So I took 2 degrees lapse per 1,000, 68 degrees off of 15 degrees standard.
Okay, good. So what he's saying, for those that didn't quite understand it, you take 34,000 feet. We'll just worry about the first two numbers here, okay? So, well, hold on. So we did it with St. George, but take this decimal point right here, okay? If we were to write out 34,000 feet, there'd be a decimal point right here. We'll always move the decimal point over 3 spots, okay? So if it's 4,000 feet, we'll be 4 degrees. Or I'm sorry, we'll just do the 4. If it's 34,000 feet, we do the 34. We take the 34, we multiply that by 2. Okay, that gives us 68 degrees. Okay, remember our standard atmosphere is 15 degrees, so we subtract 68 from 15. That gives us negative 53 degrees. Okay.
This is from a guy that got a D in math every year.
That's me too. We're in the same boat. I was starting to think I was the only one that sucked at math.
Me too. Oh, I'm so excited. An industry of people who get D's.
Oh, yay, I'm not alone.
So,
We could all go out and celebrate with an alcoholic beverage, but then we'd have to go see the bishop in a dress.
there you go.
I mean, some of us would.
My days of being a sailor are long gone now. So, when we're figuring out the deviation for MISA here, right now it's saying that over Salt Lake it's negative 51 degrees at 34,000 feet. Okay, so to figure out the deviation, what would our deviation from ISA be at this point?
Is that 2 degrees?
2 degrees plus or minus.
Well, let's see. It's 51 is warmer, so it'd be plus 2.
Good. Seems like every class there's always somebody that struggles with this conversion here. So what I always like to do is if you struggle with is it warmer or colder when we start talking about ISA, is I do the good old-fashioned kindergarten number line. Right? So this is 0. This is negative 100. This is positive 100. I mark down 53. I mark down 51. I'm moving to the right. That's a positive direction. ISA plus whatever the difference is, 2 degrees. Does that make sense? Pretty easy peasy. But if you're struggling with it, I highly recommend the number line.
Hashtag pro tip. Got it.
But anyways, so somebody want to figure out what ISA is at 45,000 feet? Somebody walk me through it.
Walk me through it too while you're at it.
I'll let somebody else step up.
Might have to go military fashion and voluntold somebody.
Not it.
Did you say not it?
I said not it.
Let's see, who do we got? Who's my victim today? Who do I not hear from the most?
I came up with minus 85.
Okay. So let's walk through it. You want to walk me through it?
So I took 45,000 feet, or 45, times it by 2.
Okay. So times that by 2. That gives us,
90.
okay.
And then subtract 15 from 90. Gives us, I guess it would be 75.
Yep, 75.
Yeah.
There we go.
75, yeah.
Now, you had mentioned that we were looking at St. George before, so how does that change the equation where the standard is 6 degrees off because 3,000 feet elevation? I mean, does that calculate in, or are we going to always use the 15 degrees?
So we're always going to go from standard. So when I was calculating St. George, I was using the 3,000 feet, but it's always the deviation from standard. Okay. So we're always looking at ISA at the altitude. So what is our standard temperature at altitude? So 15 degrees is standard at sea level. We know we're at 45,000 feet. So what is the difference between the two? Negative 75 degrees at 45,000 feet. Okay. So this would be we use our standard lapse rate to figure out what our standard temperature is at an altitude. So we'll always use sea level as our reference point, and then the deviation from that is our altitude. Does that make sense? So sea level is always the reference point. That's our zero line. Once we figure out what the standard temperature is, then we figure out the deviation from the standard temperature. That's when we use this in the equation. So this is to figure. Sorry.
Go ahead.
So this is used to figure out ISA. And then this is used to figure out ISA deviation. Go ahead, Jeff. Or Carrie, who was it?
Yeah, it was Carrie. So on that I came up with ISA plus 22.
Mm-hmm.
So 53 minus 53 minus 75, which would give you a plus 22.
Yeah, it's a difference of 22 degrees. So our ISA deviation would be ISA plus 22 degrees. Okay. Now, to show you guys why we need to figure that out, we're going to take a look at our Google Drive here. So we're done with this paper there. Let's see. We're going to go into our flight planning, and we're going to go to our performance charts. Okay. So the reason why we need to figure out our deviation from ISA is to determine the performance of the aircraft. Oops, wrong one. if you guys remember when we were talking about systems and talking about engine performance, I frequently referred to the colder it is, the better the engine perform, or not the colder, but the depending on our density, altitude, and things like that, the better or worse our engine's going to perform. So temperature, the way we figure out what we call density altitude is pressure altitude corrected for non-standard temperature. And that I understand is completely French to most of you, but in aviation that means a lot. So does anybody here race cars or have seen a car race or know anything about like drag strips at sea level versus drag strips at Rocky Mountain Raceway up here in Salt Lake? Like, does anybody?
I've never seen a race, but I did stay at a Holiday Inn once.
Yeah, there you go. So what happens is drag races done at sea level, typically they're going to be turning in much faster times than they are up here at 42,000 feet. I mean, and that's due. Remember when I was talking about that parcel of air, that column of air, and there being more feathers compacted at the bottom than there are at the top. Well, that's the same thing with engine performance. There's a whole lot more air for the engine to suck up and to grab and to use to generate thrust at lower altitudes and at cooler temperatures than there is when we're at higher altitudes and warmer temperatures. So the engine performs a lot better at lower altitudes or cooler temperatures than it does at warmer temperatures or higher altitudes. So this chart, these performance charts, if you look at the top here, it talks about our isodeviation. This chart is using an isodeviation of 10 degrees Celsius. So when we look at this chart, we can go to the flight level we're planning to fly out. And we're going to figure all this out when we're doing our planning. But let's say we're going to be flying at 35,000 feet, okay? And our weight when we get to 35,000 feet is 72,000 pounds. This is the performance we're going to use. So let's take a quick look at this. Let's just look at fuel burn, okay? Fuel burn is this top number right here, 2314. That's how many pounds each engine is going to burn at 35,000 feet for an isodeviation of 10 degrees Celsius. So it's 10 degrees warmer than standard. Okay. So 2314. Somebody remember that number just in case I forget it. 2314. Let's go to a cooler temperature now. Okay, ISA minus 10 degrees. So once again, we're looking up here, ISA minus 10 degrees. We're looking at the fuel at 35,000 feet, 72,000 pounds. Look at the difference in fuel. With the warmer temperature, we were burning, what was it, 2314?
Yes.
So we burned 200 pounds, 220 something pounds more fuel just for a warmer temperature. 20-degree difference in temperature. We're burning 200 pounds more fuel per hour, per engine. We take that 2093 and multiply it times our number of engines, 2. That gives us, what, 42,000 pounds. Or 4,200 pounds, my bad. So 4183 or 86.
Yes.
4186. Okay. So 4186 versus 2314 times 2 equals
4628.
oops. 4628. See, per hour, take 620 minus the 186. That's what, 400. 44? 34.
Or 34.
434 pounds difference. That's a lot, right? That's a lot of fuel. 434 pounds. Let's say it's negative 10 degrees. That's going to be something around 20 minutes of fuel that we just saved by being 20 degrees cooler. So you can see that it makes a big difference in our calculations when we're doing our flight planning. So that gives you guys a practical, put all these puzzle pieces we just talked about together. Does anybody have any questions on any of that we just talked about?
I do. So when you're flying in cooler air temperatures at altitude, the air is denser, correct?
Typically, yeah.
So I see how the engines are operating more efficiently, burning less fuel, but you're pushing through denser air. What happens to your airspeed? Does it take longer to get through that dense air using more power, or does that make sense, the question?
Yeah.
Seems like you're using more fuel to get through the dense air.
There's a trade-off here, and the trade-off is wind direction. Yes, you technically have more friction on the aircraft, but the performance, the benefit to the engine performance is greater than that of the friction. Does that make sense? And then when we talk about air, wind direction, that's also going to play a part in how far we're able to get, right?
Yeah, that's a whole nother factor. Just
right.
Assuming that the winds aloft were the same,
Uh-huh.
either, just for this scenario.
For this scenario, yeah. So, so like I was saying, it's in that case, in that scenario alone, just the temperature difference alone being the only variable, the performance of the engine outweighs the loss due to the friction, the amount of friction on the aircraft, by a drastic difference, right?
Yeah.
20 minutes of fuel, basically, in one engine. So 10 minutes across 2 engines.
Thank you.
Mm-hmm.
Gira, you had said earlier, you stated something followed by pressure altitude. Is pressure altitude corrected for non-standard temperature? What was that first part?
So density altitude is pressure altitude corrected for non-standard temperature.
Thank you.
Mm-hmm. So when we talk aviation, there's 3 separate altitudes that we will figure when we're planning our flight. For us, we only care about the one, really, and that's going to be density altitude for engine performance, right? So I'm trying to figure out a way to say this without like adding a whole ton of confusion to what we've already talked about. And I sometimes need to use this to help me say it more clearly. So, okay. So, in the cockpit, let me go back to our lesson plans here. So, this very last page, we saw this 29.92. Okay. Pressure altitude is altitude corrected for non-standard pressure. Okay. So what we're referring to there is that as the barometric pressure fluctuates, it goes higher or lower. Okay, the way they used to measure the amount of pressure in the air is they literally took this tube and filled it up with mercury and then measured how many inches high the mercury would rise and fall. And that's where we get the term inches of mercury. Okay? It's kind of like a thermometer, right? But measuring pressure. So they'll take this vial and they'll measure the pressure. Let's go to our aviation charts really quick. When we look at our aviation charts, you can see sorry, I'm trying to find the right chart here. Okay, right here. Okay, you can see these tan lines. Remember we talked about these high pressures and stuff. The H in the blue is high pressure, cold air, right? L, low pressure, the warmer air. This is a cold front. This is a warm front right there. This is an occluded front, right? Or I'm sorry, this is a stationary front. The purple, you'll see a purple line. That's an occluded front. These dashed lines, these are troughs. But you'll see these light tan lines on the screen here. And there's a number associated with these tan lines. So think of this as like a topographical map, but instead of mapping altitude, it's mapping pressure differences. So the pressure in this area, right here, right in the center of the map, is 1012. Okay. You can see that the pressure, the standard pressure, once again referring to standard pressure, is 1013. So our deviation from the standard pressure is 1 on the hectopascals. On the inches of mercury, let's see. Let's go back to our textual. Oops. Look at our METAR here. Let's use St. George as our reference point here. Our standard pressure is 29902. We are at 29079. Okay. So for every 1,000 feet, or I'm sorry, let me rephrase this. For every 0.1, so standard being 290.902, and we are currently at 290.79. Our deviation from standard here is going to be 12, 8, so 0.13. Okay. Our difference here being 0.13, our altimeter, let's say our altitude at St. George is 28,084. Our pressure altitude, taking this into consideration, the amount of pressure at St. George, we would add, because it's more dense, it's more pressure, right? We would add to this 1,000 for every 0.1. It'd be 1,300 feet, basically. So 1,300 feet. The aircraft is going to perform to 42, as if it were at 42,064. Now we take our non-standard temperature, and remember that was 20 degrees. We were ISO plus 20. We would take ISO plus 20, and that would be our density altitude. So 20 degrees, we're talking, we're going to be adding on, 10,000 feet. So density altitude in St. George is going to be something like that. 14,264. So the aircraft, even though we are only at 2,884 feet, the aircraft is going to perform like it's at 14,300 feet. You can see why Flagstaff, when it's 85 degrees but 7,000 feet above sea level, why at 85 degrees we're going to be bumping passengers, right? Because the engine performance is going to be drastically different, way more poor. That's a huge difference, right? That's pretty much the concern. So when we correct for non-standard pressure and then correct for non-standard altitude, we can see a huge difference in performance. Now, I may be a little bit wrong. It's been a long time since I've actually done this calculation, but the point I'm trying to show you is that when we correct for non-standard pressure and get our pressure altitude, then correct for non-standard, or pressure corrected for non-standard temperature, it's even bigger, sometimes even bigger gap. Than we initially thought. So, you know, did any of that make sense?
Clear as mud.
Kind of. I think it's something that, like, once I start having stuff to do with it, it will be easier to do.
Yeah.
Like, I see where you're getting the numbers from, but until I have, like, kindergarten worksheets of it, I don't know if I can commit it to memory.
And we're gonna get there, I promise. We're getting pretty close to that point.
Like, how close?
Well, we're midway through our week 4, and week 6 is all practical dispatch applications. So next week around Tuesday or Wednesday, I want to say probably Wednesday, we'll be finishing the meteorology section. And then Thursday, Friday, and maybe Monday, we'll talk about like DRM and some of the other things, just kind of cleaning up the rest of the sections we need to cover. And then it's all going to be dispatch practical applications for the rest of that week. Then weeks 7 and 8 are all flight planning. And we're just going to go through flight plan after flight plan after flight plan after flight plan. And it's all going to be in a classroom because it would be absolute hell trying to explain this online over the internet.
And you're saying that's not going to be absolute hell in class?
Much less. Far less of a problem.
Hell adjusted for density altitude.
Exactly. And we're going to be maybe freezing it over, right? No, but believe it or not, we're like more than halfway through the course, and we're getting into the final stretch. This is when everything's going to start coming together, and you're going to be like, oh yeah, that's why we talked about that. Oh yeah, that's why we talked about that. So anyways, once again, we're kind of at a good stopping point. I don't want to jump into the next thing that we had to cover. I thought, for some reason, I thought we were a little bit further along and it would maybe take a little bit less time tonight than it did, but it was time well spent. And with meteorology, you cannot go too slow through meteorology. It's a complex, very difficult part to understand and to grasp. And but it's a big part of what we do. So we want to take our time through this section. Anyways, so that being said, we'll call it a night. Unless there's any other questions.
Just how quickly will you be getting this one uploaded to the YouTube channel so that I can watch it 3 or 4 more times?
We will. I will have it converted, and I'll have it up tonight.
Perfect. Thank you.
It's really weird. So
did you say there were 3 types of atmosphere or altitude?
Yeah, 3 different.
Density, altitude,
So
pressure,
you have
altitude.
You have actual altitude. So, like in Salt Lake, we're at 4,228 feet at my house. And then once we adjust for non-standard pressure, we have our pressure altitude. So all of a sudden, let's say 5 degrees, or I'm sorry, the pressure is, 1,000-foot difference. All of a sudden, we're at 5,000 feet. And then density altitude, we correct for the pressure altitude, corrected for non-standard temperature. All of a sudden, we're at 8,000 feet. So in aviation, there's 3 different types of altitude, and all are important. But in dispatch, we only really care about density altitude. I mean, actual altitude and density altitude is all we really care about. The pilots have to worry about pressure altitude because of their altimeter in the cockpit. But anyways. Yeah.
All right, cool. Thanks, Garrett.
Yeah, no problem. Yeah, like I was saying, this go-to meeting, for a little while there, the recordings were converted already as soon as I closed and ended the meeting, the recordings were already converted. But for some reason, it went back to its old way on my other computer. It went back to its old way of having to convert the entire thing. So it just depends on what happens when I close the application. If it's already converted or not is how quick it'll be uploaded to YouTube. So, anyways. Alrighty.